Hello and welcome to our new videocast for the release 2010. Today I am going to present the latest changes in our source code analyzers Astrée and RuleChecker. Let's start with Astrée. Astrée is now officially available for C++ analyses. What that means and what is possible will be shown directly after this feature overview. We improved our RxML Converter a lot and also our AAL export for command directives. I will introduce a new directive Astrée attributes and show you the enhanced control and data flow view. And of course, we also worked on our RuleChecker. There, a new rule set SEI CERT for C++ will be available, and we enhanced the rule sets AUTOSAR C++ 14 and MISRA C++ 2008. But now, let's directly start with Astrée for C++. As I said, starting this release, you will also be able to analyze C++ code with your sound analyzer Astrée. Also, mixed projects with C and C++ code are possible. But let's not talk too much, but show it using one of our example analyses. Here we have a couple of small code examples that demonstrate nicely what Astrée can analyze. The first example shows that Astrée supports C++ templates and operator overloading. It defines an array template class and creates an instance of that template that can store up to 10 integer values. The code then iterates over the array using a for loop with an inappropriate loop condition. The loop is erroneously entered 11 times, and in the 11th iteration we call the index operator with index 10. This leads to an out-of-bounds array access, in this instance, of the array template, which can only hold 10 elements. Astrée finds and reports this runtime error. In the second example, we can see that Astrée is able to analyze new and delete operators, and also finds and reports C++ specific runtime errors like pure virtual function calls. By constructing an object of class derived, we first invoke the constructor of class base. By calling the store method of base, this constructor also indirectly calls the method count. In base, the count method is declared pure virtual, which means that it has no implementation at this point. Executing this code will lead to a crash at runtime. As you can see, Astrée detects and reports such errors in your C++ code. The third example shows a dangling pointer problem in C++ code. The code creates an object inside of an if block and assigns its address to the pointer p. This pointer escapes the scope of the if block, but the object it points to is deleted at the end of that block. Therefore, the pointer is dangling when we reach the return statement, and the method getTouches is called with an invalid thisPointer. Astrée detects and reports both the dangling pointer in line 112 and the resulting invalid thisPointer in the getTouches method in line 93. The fourth example shows a very subtle C++ specific dangling pointer problem. The programmer expects that below up is a variable of type bool. But auto-type deduction for that variable unexpectedly creates a reference to a temporary object. This temporary object is immediately deleted and consequently the reference in below up is dangling. Astrée detects this problem and warns about uses of the dangling reference. Note that by writing explicitly bool instead of auto in the declaration of below up, this problem would not occur. In that case, Astrée would detect that below up is a proper bool variable and would not raise a false alarm. The fifth example shows a class with overloaded constructors, one of which is using an initializer list. In the example 5 function, we construct a sum numbers object with an integer and a Boolean argument, and we expect that we call the first constructor. But since we're using curly brackets here, the compiler prefers the second constructor that takes an initializer list argument. The integer and Boolean arguments are implicitly converted into doubles to fit the initializer list. As a consequence of calling the unexpected constructor, the variable my_i is not initialized, contrary to the expectations of the programmer. Therefore, the following call of the getInt method reads from an uninitialized variable. Astrée detects and reports the uninitialized read problem. In the 6th example, we have a class thing and a class sum that inherits from thing. The method f in class sum attempts to perform an invalid dynamic cast on a global pointer to an object of class thing. This code compiles without warning, but the dynamic cast in this example will throw a bad cast exception. The exception will unexpectedly abort program execution at this point. Astrée detects and reports the bad cast exception. Let's get to our improved RxML converter. We worked hard to facilitate your workflow with Astrée's RxML Converter. It now supports a fully automatic integration analysis for OSEC and AUTOSAR projects. Let's directly look at it in Astrée itself. As you can see, we provide an RxML example, which I will use for the demonstration. When opening the project, we are directed to the preprocessor view with AUTOSAR chosen as operating system. When setting up an AUTOSAR project, an RxML file can be provided to Astrée. Astrée then reads the project configuration and automatically generates an analysis wrapper and application-specific stub functions. The RxML file should contain the information about system configuration, about called tasks and applications, and used cores. Using the option Generate Analysis Wrapper, Astrée generates an analysis entry function called Astrée main, which is used as the analysis entry point. If the option is not activated, no main function is created, which leaves you the opportunity to provide one yourself. After clicking Preprocess and Start Analysis, we can see that the concurrent analysis runs completely automatic. This already leads us to the Astrée annotation language and our new directive. Comment annotations now automatically contain the corresponding alarm location after commenting an alarm. There is no need in rerunning the analysis to get the exact location for the comment. This can also be very helpful when importing comment annotations to a project. And we have a new directive, Astrée attributes, which can be used for excluding files or functions from the project coverage or raise an alarm at the calling function instead of the called one. I prepared a small example to show you how the usage of such a directive could look like. In the file attributes file, an Astrée attributes directive using the attribute coverage ignore is inserted at the beginning of the file and hence is applied to all functions contained in that file. Consequently, the whole file is excluded from the project coverage. In the file attributes fun, the directive is inserted on function level, once again with the attribute coverage ignore. This excludes the functions containing this directive from coverage. As we can see, the body of the if statement will never be reached. In the overview reachability tab, we see 100% coverage for the file attributes fun, since the function we just saw is successfully excluded from project coverage. Also, the file's attribute file is successfully excluded from project coverage, displayed by 0 statements that were not reached. The second attribute you can use in the Astrée attributes directive is raise at caller. Using this attribute, Astrée will raise an alarm in the calling function. Again, we have an example on file and on function level. At file level, the directive is inserted at the beginning of the file to apply it to all functions in that file. When we look at the caller, in this case the main function, we see that the alarms are raised on the calling side. On function level, there are 3 functions: helper, raise at caller function fun0, and raise at caller function fun1. A directive is inserted in the helper and in fun1. Inserting the directive into the helper function leads to an alarm in the calling functions, which are in this case fun0 and fun1. Since we also added an Astrée attribute directive in fun1, the alarm is transferred again to the main function, which we can see here. If we now look at such an alarm and click on the call stack, the different calls are listed there with the cause of the alarm as last entry. As you can see, this also works for nested calls. Now that we saw the usage of the directive, let's look at the improved behavior of the comment directive. When classifying and commenting one of the alarms, the comment directive, as you can see, is directly created at the specified location. No need to rerun the analysis. We renamed the data flow view to global data flow and enhanced the control flow view. The corresponding tab in the overview now also shows the location and optionally function in which a variable is defined. The control flow view now shows the call side, application, and core additionally to the caller-callee relationship. Clicking on the entry does now lead us directly to the source code location. Now that we saw the most important news about Astrée, we also want to take a look at our RuleChecker. We enhanced the rule sets AUTOSAR C++ 14 and MISRA C++ 2008 a lot. Additionally to that, we now also have a new rule set SEI CERT C++. As always, there are more news than I can present in a short video like this. To find all news, please visit our website www.absint.com, and if you have questions or are interested in one of our tools, write a mail to info@absint.com.